Right, so we're going to look at free body diagrams. Okay, and free body diagrams are used to represent things involving force. Okay, so anything that involves the force or the motion of an object with mass, we can represent with a free body diagram. I like to think of it as a way for me to involve engaging in art at any point in time. Okay, so rather than having to draw cars or humans or sleds, we just represent everything as a box. We don't care what it looks like. What we care about is its mass and the forces that are applying on it. It's really important to remember that force is a vector quantity. Okay, now vectors can be added, subtracted, but it's really, really important to know that direction is important. Okay, so as you go further with your physics, you'll dabble more with that, but at this stage you're probably going to be dealing with up, down, forward and backwards. You will go further into that where you'll be dealing with angles and all sorts of stuff using trig. But for now, force is a vector, so you just need to be aware that if you've got something moving forward, a force applying forwards and a force applying backwards, direction is important, and obviously it's really important to understand that friction always opposes motion. So if an object's moving forward, friction's applying backwards, it never goes with the motion. And in the case that friction is greater than the force applied on the object will not move. So free body diagrams, in these diagrams, all forces are represented, not just the ones, so I'll give you an example in a second, but all forces that are present are represented, even if they cancel out. So let's have a look at our first example here. So the first example I've got is one that involves me sliding my 3.6 kilogram laptop across the bench. So again, with a free body diagram, I'm going to draw my bench, very artistic, and I'll draw my laptop. Very artistic. Now, I'm going to write in my mass, 3.6 kilograms, and I'm going to represent all forces present with an arrow. Now, I haven't been told which direction my laptop is being slid, so I'm just going to assume that that is my direction. That's not the only force it's applying. Now, obviously, we've got gravity applying, which is going to be 36 newtons down, because 3.6 times 10, assuming this is being done on Earth, and the reaction force being applied upwards. Now, there's a problem with this diagram. The arrows don't make sense. If we look at the size of the numbers, 36 newtons, and 10 newtons, all the arrows are about the same size. That's a problem. The arrows, there's no scale that I need to follow, but they should represent a similar ratio. So this arrow needs to be far, far shorter. Okay, so to represent 10, I really should have an arrow that looks like that. Okay, are we clear? So our free body diagrams represent all the forces present. Even though these forces cancel out and really don't have any impact on where this laptop's going to go, it's important to acknowledge them. Okay, and as you go further into friction, you'll understand why that's important. So let's look at B. It's the same object, so the laptop. It accelerates at 2 meters per second squared. We're going to demonstrate this as a free body diagram. There's a little bit in this because before we start doing anything with our free body diagram, we need to acknowledge that we've got Newton's second law at play. So Newton's second law says F equals ma. So I'm trying to find my frictional force here. Oh, sorry. I'm trying to find my driving force. A little bit tricky here. So I don't know what my force is, despite the fact they've given me my force before. I don't know what the net force is. I do know my acceleration is 2, and I know my mass is 3.6. So 7.2 newtons equals F. Now what that really equals is not any one of these forces, but my force net, the total force. So when I add 10 to my frictional force, or subtract my frictional force from 10, I will find that my result is 7.2 newtons. So how do I find my frictional force? Because I'm missing this arrow. I'm missing the arrow on the back. I don't know what the size of this arrow is. I know it's going to be less than 10, but I don't know the size of that arrow. So I think back to what I did in the previous example where I had F net equals I'm just going to call it my driving force, FD, which is 10. okay, my driving force FD, make that a little d so it's consistent, minus my frictional force. Cool. So that's what's going on. I've got my 10 newtons minus some force we don't know about because it's in the opposite direction will give me 7.2 newtons. So 7.2 equals 10 minus FF. I'm going to rearrange that to get FF by itself on one side and numbers on the other side. So FF, I should show you how I'm doing this, but I'll do it a bit quick. 10 minus 7.2 is 2.8 newtons. That tells me that my frictional force is 2.8. So if I was to represent this as a new diagram, again, I'd write in my 3.6. I'd represent my 36 newtons applying up, my 36 newtons applying down. I'd represent my 10 newtons applying across. It's a little bit too big, that arrow, but that's okay. And I'd represent my 2.8 newtons applying back, okay? And that would be a complete free body diagram for that situation. So there can be a little bit of that. You just need to think about the fact that, a reminder that forces are vectors. Forces are vectors, which means that direction matters. You might need to add or subtract depending on the direction two different forces are applying. All forces, including gravity and reaction forces, need to be included in our free body diagrams. And the size of the arrow should represent the scale or the ratio of the forces being involved, okay? Hopefully that helps. These are really, really useful tools, and they'll become more useful as you get further through your physics, but they simplify rather complex problems involving many vectors combining with each other. Good luck.